So we're finally on to our last technique of integration that we're going to talk about, which is partial fractions. So this is going to be a way for us to take rational functions and split them up so that it's easier for us to take the integral. So if we have a rational function written like we have the one here, 2 over x minus 3 plus 1 over x minus 4, this is pretty straightforward to take the integral of because we can take the integral of each of our terms. And since we've got nice linear factors in the denominator and on both of these, that denominator does not have a coefficient on x, so du is going to be dx. If we did substitution on this first one, we get 1 over 2 du. If we did a similar substitution on the second integral, we get 1 over u du. So both of them would end up being the natural log. Actually, let's make sure we've got our colors going here. And this would be u would be x minus 4. And if we wanted to, maybe to make things a little easier for us, we'll name this one v. That dv is equal to dx. And then this would also be dv. So then going back to the orange pen, we get 2 times the natural log of the absolute value of u plus the natural log of the absolute value of v plus our constant term, and then, substituting things back like we do, we get the natural log of the absolute value of x minus 3 plus the natural log of the absolute value of x minus 4 plus c. So it's not too bad to take the integral of that. And we'll do several of these, so you'll start to notice that if you've got a linear factor that's in your denominator and there's no coefficient on the x, we don't have much we have to do in terms of the substitution because du is equal to dx, and that's usually why we need to do substitution, is that there's some sort of coefficient that we need to add into our integral. We don't have to do this here, so we really can often go straight from here to right here. The just our two, small rational equations and then taking the integral of those. Now, this isn't normally, though, how we see rational functions. Normally, what we see with our rational functions is that we've gotten a common denominator and we have added the numerators. So here we are getting a common denominator of x minus 3 times x minus 4. And so the numerators end up being 2x minus 4 as sort of that first fraction, and then x minus 3 for our second fraction. And then normally, we add those like terms on the top of our fraction, and this is normally how we see a rational function. It normally looks like that, or even a little more, sort of normally how we see it, we would have the denominator multiplied out. This is probably a little bit more how we're used to seeing a rational function. And what we're going to want to do is take our rational function that's written this way right here, all multiplied out, and we're going to want to write it like it's written right here. Because if it's split up like that as two separate smaller rational functions added together, then it's pretty easy to take the integral. Down here, where everything's all multiplied out and added together, not so much, not so easy. So what we're going to have to do is take this process that I just wrote out here, these steps of where we got a common denominator, then we multiplied the tops of our fractions to get that common denominator and the bottoms of our fractions, and then combined our like terms and multiplied everything out. We have to go backwards here. So how are we going to do that? So let's take a rational function that we don't know the integral to. Let's take this guy right here. X over 2x plus 2, or I can't read. X over x squared plus x minus 2. There we go. So our method here, and this is called partial fraction decomposition. And I kind of actually like this term, especially the decomposition part of it, because we're going to take something, that's written nice and compactly like this, and we're going to split it up and decompose it into two separate functions or more, depending on what we need. We'll see some that need more. Two or more separate smaller fractions that are added together. So our first step on this is to take our denominator and factor it. So we're starting with x squared plus x minus 2 in our denominator. All of our denominators will factor some sort. Okay, there we go. So now we've got our denominator factored. That's that first step, all we have to do. Then the second part is to write the partial fraction decomposition. So what that means is that we're going to take our fraction with the factored denominator, and what we'd like to do is split this up as a fraction that has that first half of that common denominator and the second half of that common denominator, and then it's going to have something for the numerator. And we're just going to call them capital A and capital B. And we're going to figure out what those need to be. So back up here, again, what we're trying to figure out here is that we've got our factored rational function like right here, and we want to go back to this form where it's two fractions added together. So we're trying to figure out what's going to be up here in these numerators, so that when we add those two fractions together, we'll get back to this original fraction. So this is the partial fraction decomposition. This is that whole step that we're just kind of splitting it up right here. Now we're going to take this partial fraction decomposition. I'm going to copy and paste it. I'm going to paste it down here. And we want to clear out our denominators. So what we're going to do is that we're going to multiply through by the least common denominator. And it's actually really easy to find what the least common denominator is in this, because it is always going to be what is sitting on this original fraction right there. That's our least common denominator. It's x plus 2 times x minus 1. That is our least common denominator. So it's kind of nice. There's no thinking involved here. I was like when we can do a little math and it can be a little bit brainless. So we're going to multiply each of our terms by this least common denominator. And what this is going to do is clear out all of our fractions for us. It's going to clear out all of our denominators. So here that x plus 1 or x minus 1 cancels with the x minus 1. Here the x plus 2 cancels with the x plus 2. Over here, both of these cancel there. Yay! So what we're left with is that x is equal to a times x minus 1. And where does that come from? We've got our a sitting right here and our x minus 1 right there. Those are being multiplied. Plus our b times x plus 2. So what we've got is kind of a funny little equation here. And we can solve this for the coefficients. And by coefficients, I mean that capital A and capital B. So the relationship that we've got right here, that x is equal to a times x minus 1, if we multiply that out, if we FOIL that out, we get a times x minus a. And similarly, if we take b and multiply that through, FOIL it out, because we're trying to solve this. We're trying to figure out what a and b are. And to do that, we need to get rid of these parentheses, 2b. And I'm going to rewrite things just a little bit here. I'm going to rewrite this as x plus 0, meaning that it doesn't have a coefficient. Then I'm going to change the order that I have my terms over here written. Minus a plus 2b. So if we take a look at this, if we were able to combine like terms, if we knew what a and b are, if we knew a and b, we would add those as coefficients here, and we should get that they're equal to x. Similarly, if we knew what a and b are, if we did minus a plus 2b, we should get 0, because those are constant terms. Those are parts without our x value. So if we take that x, it needs to be equal to what we get from ax plus bx. And we also need here to get 0 when we add negative a plus 2b. I'm going to take this one that we have in green here and rewrite it just a little bit, because this is what we do when we combine like terms, right? We add those coefficients together and multiply by our x value. And our coefficient here is 1. So what we are saying is that when we do a plus b, we better get 1. We need to get a coefficient of 1. So 1 needs to be equal to a plus b. So what we've basically gotten here from doing this process, and this is a process we'll do several more times in class, is that we've got ourselves a little system of equations. We need to figure out what values for a and b, when we add them, we get 1. And also, when we do negative a plus 2b gives us 0. So it might be a while since you've solved a system of equations. I'm going to take the second equation and I'm going to add a to both sides to get that a is equal to 2b. And then I'm going to substitute this a being equal to 2b into the first equation. So I'm solving with substitution. This is also one you could solve with elimination if that term rings a bell. So we get 1 is equal to 2b plus b. So 1 is equal to 3b. So dividing both sides by 3, we get 1/3 is equal to b. And then we also have this relationship that we just wrote up here, that a is equal to 2 times b. So a is going to be equal to 2 times 1/3. So it's 2/3. So what is it that we found here? So we figured out what a and b need to be so that when we add them up, we get 1. And we just do a plus b, which is right here. We do a plus b, we get 1. And if we do negative a plus 2 times b, we get 0. What we also figured out here is that our original quadratic, or not quadratic, rational function, so this original guy up here, our x over x squared plus x minus 2. So x over x squared plus x minus 2 is equal to, remember we were trying to split this up as our first denominator plus our second denominator to make sure that I have these lined up right. And we wanted to figure out what a and b needs to be so that when we add these two fractions, we get back here where we started. Well, we figured out that a needs to be 2/3 and b needs to be 1/3. So what we've discovered is that if you have 2/3 times 3, actually I'm going to leave it as 2/3 up there on the top. If we add these two fractions together, these two fractions right here, if we get a common denominator and add them together, we are going to get this rational function. So our common denominator would be 2/3 times x minus 1 over x plus 2 times x minus 1, 1/3 times x plus 2 over x plus 2 times x minus 1. And so we get 2/3 x minus 2/3 for our first numerator, 1/3 x plus 2/3 for our second numerator, and over our common denominator. And if we combine our like terms, we get 2/3 x plus 1/3 x, that's 1x. And then our minus 2/3 and plus 2/3, that's a 0. So we exactly get that rational function right there. So what we figured out is we figured out how to pull that apart as into two smaller fractions. And why we like to do this, why we want to do this, is this is going to turn this into an integral that we can take. So we can rewrite this integral as 2/3, whoops, got too many fractions here, 2/3 over x plus 2 plus 1/3 over x minus 1 dx. And then I'm going to rewrite this just a little bit, just for our own sake, to help us take our integral. So that 2/3 that's up on the top, you can write it out in front as a multiplication. Same with that 1/3. I don't want to actually multiply those through on my denominators at all though, because I want to treat those as coefficients. I want to have that 2/3 and actually bring it outside of my integral, and that 1/3 and bring it outside of my integral. And so now hopefully what you see right here is that we're back to a very, very similar integral to what we had way up here when we were doing this original integral. And we talked about that, each of these are pretty easy to do because when we do the substitution, we just get 1 over u or 1 over v, and it's just natural log. That's the same thing down here because we don't have a coefficient on either one of those x's. So we get 2/3 natural log of the absolute value of x plus 2 plus 1/3 natural log of the absolute value of x plus minus 1 plus our constant. And that's our integral.